that is del by del t into rho Vx is equals to minus of del by del x into rho Vxx plus p in plus tau into xx plus del by del y. As I have said that for yx direction thickness is 0, that is pressure term will not come here, only shear stress, that is tau, that is remains here, and for similarly that is for zx direction. So we are now discussing it is density into Vy into Vx plus tau is in Yx plus del by del z into rho into Vz into Vx plus tau into zx plus rho into gx, that is the forces that is acting in x direction. Similarly we are now simplifying the terms, and we can differentiate the terms with respect to x, that is density into velocity. As I mentioned earlier, we have to now apply here simply mathematics, that is we have to differentiate the terms one by one. That is, first we can differentiate the term with respect to density keeping velocity constant, and second we can differentiate the term with respect to velocity keeping density constant. We can break the terms like rho del by del y into rho Vy into Vx plus del by del y into tau Yx plus del by del z into rho Vz plus rho into Gx, that is the gravitational force, that is it is constant, that is it is not changing with respect to x or y, only it is in x direction. That is why we have representing the gravitational accelerator, that is the suffix, that is x. Now we can further simplify the terms, that is del by del t into rho Vx plus del by del x into rho Vx into Vx plus del by del y into rho Vy into Vx plus del by del z into rho Vz into Vx is equals to minus of del p upon del x minus of rho del by del x into tau xx plus del by del y into tau yx plus del by del z into tau zx plus rho gx. So now we are considering the two terms and represented by left hand side and right hand side. Left hand side term that is del by del t into rho Vx plus del by del x into rho Vx into Vx plus del by del y into rho Vy into Vx plus del by del z into rho Vz into Vx. We can differentiate it with respect to, as I have said, that is with respect to velocity keeping density constant and with respect to density keeping velocity constant, but actually it depends upon the fluid, that fluid is changed or that density of the fluid is changing with respect to directions, or only just velocity is changing with respect to directions. So RHS term is now minus del p by del x minus del by del x into tau xx plus del by del y into tau yx plus del by del z into tau zx plus rho gx. Now we can further simplify our LHS terms. We can write it that LHS is equals to del by del t into rho into Vx plus del by del x into rho Vx into Vx plus del by del y into rho Vy into Vx plus del by del z into rho Vz into Vx. Here we can put the differential terms and we can further simplify it. We can also simplify it for spherical coordinates and cylindrical coordinates, but actually here in this video we can only know the simplification for Cartesian coordinate system, that is in x, y and z direction. So we can further simplify it, that is density into as I mentioned here, density is constant, so del Vx upon del t plus Vx, that is del rho by del t. As we are keeping velocity is constant, we are differentiating it with respect to density. So plus rho Vx into del Vx by del x. Actually, as earlier mentioned, there are three terms. So we are differentiating it one by one, keeping other two terms as constant, differentiating one term and keeping other two terms are as a constant. So we are getting our equation, that is del rho density into del Vx upon del t plus Vx into del rho by del t plus rho into Vx. Keeping these two terms constant, we are further differentiating it with respect to x, that is del Vx plus del x. So we can again write this equation for simplification and for study, that is del by del x into rho Vx plus Vx into del by del y into rho Vy plus del rho Vy into del Vx upon del y. Actually, this is a simple differentiation and all we need to know, that is mathematics. Plus Vx into del by del z into rho Vz plus density into Vz, that is del Vx upon del z. As I have discussed earlier, we are seeing it with respect to velocities, that is in x, y and z. So we are differentiating it as per our equations. So actually here the terms that is come from differentiation. So that is further simplification. We are saying that is density into del Vx upon del t plus rho Vx into del Vx upon del x plus rho Vy into del Vx upon del y plus rho Vz into del Vx upon del z plus Vx into del rho upon del t plus Vx into del by del x into density into viscosity into velocity, plus Vx into del by del y into density into velocity in y direction plus Vx into del by del z in density into z direction. Now we can further simplify it, is equals to rho into del Vx upon del t plus Vx into del Vx upon del x plus Vy into del Vx upon del y plus Vz into del Vx upon del z. Okay, so we can simplify the terms further, and here we can next also we can simplify it as a, and we can simplify and we can write it as LHS, that is left hand side term separately and right hand side term separately. So further I mentioned that Vx into del rho by del t plus del by del x into rho Vx plus del by del y into rho Vy plus del by del z into rho Vz plus del rho by del t plus del by del x into rho into Vx plus del by del y into rho into Vy plus del by del z into rho into Vz is equals to 0. That is, we are continuing the equations, and now we can simplify the term, that is, as I said, that is in LHS term, that is left hand side term, and RHS term, that is right hand side term. So left hand side term is equals to density into rho Vx upon rho del t plus Vx into del Vx upon del x plus Vy into del Vx upon del y plus Vz into del Vx upon del z. Now we can write right hand side term, that is, actually in the above equation we simplified the terms by differentiating and arranging it here the molecular momentum flux, that is equal to tau xy plus plus p into thickness into xy. Here that is, it represents that y momentum is positive in x direction. Similarly it represent for tau yx, and similarly it also represent for tau zx. Actually here thickness for x is equals to if thickness is equals to 1 when the suffix are equal, that is thickness is equals to 1 for del xx is equals to 1, and if del xy and del yz thickness is equals to 0, so therefore we can neglect here p term because of thickness is equals to 0. Similarly, we can prove it for Cartesian coordinates, spherical coordinates and cylindrical coordinates also. So here we are simplifying the terms, that is RHS and LHS, and then we are writing it together, that is density into del Vx upon del T plus Vx into del Vx upon del X plus Vy into del Vx upon del Y plus Vz into del Vx upon del Z plus Vx into del Z del Vx upon del Z. And that is our left hand side term, and then we can write the right hand side term, that is equals to, that is minus del px minus del px minus del px minus, actually here we are simplifying the various terms, and for in this video we are only deriving for Cartesian coordinates. Similarly, we can derive for cylindrical coordinates also and spherical coordinates also, but it is quite complex to derive for cylindrical coordinates and spherical coordinates. So our right hand side term, that is minus del p upon del x minus del upon del x into tau xx plus del upon del y into tau yx plus del upon del z into tau zx is it plus rho into gx, that is the gravitational forces we are considering here for equation of motion. Is equals to, we further simplified our terms, that is del by del t into rho vx is equals to minus of del by del s into flux at xx plus del by del y into flux at yx plus del by del z into flux at zx. Here flux at xx means and flux at yx means y, we represent that is y momentum in positive x direction, that is the meaning of suffix here. So this is equation 1. Actually here in this video, as I already said, that we have derived it for Cartesian coordinates, and then we can write the terms together that we have derived in the above pages. So equation of motion in Cartesian coordinate. So density into del Vx upon del T plus Vx into del Vx upon del X plus Vy into del Vx upon del Y plus Vz into del Vx upon del Z. That is the left hand side term, and then right hand side term, that is minus del P upon del X minus of bracket del by del X into tau xs plus del by del Y into tau yx plus tau means here shear stress plus del by del z into tau zx plus rho gx. That is the gravitational forces in directing x equation of motion, and this is represent our x equation of motion. That's why we are taking with respect to x, that is tau xs, tau yx and tau zx. Then similarly we can write it for y equation of motion and z equation of motion. For y equation of motion, we can write it as density into del Vy upon del T plus Vx into del Vy upon del X plus Vy into del Vy upon del Y plus Vz into del Vy upon del Z is equals to, that is our right hand side term, that is minus del P upon del Y minus bracket del upon del X into tau xy plus del by del Y into tau yy plus del by del Z into tau zy plus rho gy, that is the gravitational forces acting in y direction, means we are taking with respect to y direction, that is y equation of motion. Similarly, we can write it for z equation of motion, that is density into rho vz upon del T plus Vx into del Vz upon del X plus Vy into del Vz upon del Y plus Vz into del Vz upon del Z. Then we can write it the right hand side term, that is minus del p upon del z minus of bracket del upon del x into tau xz plus del upon del y into tau yz plus del upon del y into tau yz plus del upon del z into tau zz plus rho g z. That is the z equation of motion. That's why we are taking as tau xz, tau yz and tau zz. Similarly, we can write it for cylindrical coordinate systems also and spherical coordinate systems also. Now we are going to write, actually we didn't derive for cylindrical coordinate and spherical coordinate in this video. We only derived the equation of motion of Cartesian coordinates in this video. So actually here our coordinates also get changed. In place of x, y and z we come to know r, theta and z. So we are write it for r equation of motion, that is density into del Vr upon del t plus Vr into del Vr upon del r plus V theta upon r into del Vr upon del theta plus Vz into del Vr upon del z minus V square theta upon r. The whole term represents the left hand side term. Then we can write for right hand side term, that is minus del p upon del r minus bracket of 1 upon r into del by del r into r into tau rr plus 1 upon r into del by del theta into tau theta r plus del by del z into tau zr minus of tau theta upon r, the bracket close, plus rho gr, that is the gravitational forces acting in r direction, that is the r equation of motion. Similarly, we can write theta equation of motion and z equation of motion. Now we are going to write for theta equation of motion, that is rho into del v theta upon del t plus Vr into del v theta upon del r plus V theta upon r into del v theta upon del theta plus Vz into del v theta upon del z plus Vr into V theta upon r is equals to, now we are going to write the right hand side term, that is minus 1 upon r into del rho upon del theta minus of bracket 1 upon r square del upon del r into r square tau r theta plus 1 upon r into del upon del theta into tau theta plus del by del z into tau z theta plus tau theta r minus tau r theta upon r. This plus rho into g into theta, that is the theta equation of motion, that is the forces acting in theta direction, plus rho into g theta. Similarly, we can write it for z equation of motion, and we can also derive for spherical coordinates. But they are the quite complex equations. If we consider the complex flows, then we can consider the above equations, that is for cylindrical coordinate also and spherical coordinate also. But actually it all depends upon our system. Now for z equation of motion, that is density into del r into vz upon del t plus Vr into del Vz upon del r plus V theta upon r into del Vz upon del theta plus Vz into del Vz upon del z is equals to, this all represent the left hand side term. Then we can write it for right hand, we can write the right hand side term, that is minus del p upon del z minus bracket 1 upon r into del by del r into r into tau rz plus 1 upon r into del by del theta into tau theta z plus del upon del z into tau zz plus rho gz, that is the z equation of motion. And here we are considering the forces in z direction. Similarly, we can write it for spherical coordinates, and for spherical coordinates, in place of x, y and z we consider r, theta and phi in spherical coordinates. So equation of motion in spherical coordinate system. First we are going to write for r equation of motion, then we are going to write for theta equation of motion, and then we are going to write for z equation of motion. So for r equation of motion, del into del Vr upon del t plus Vr into del Vr upon del r plus V theta upon r into del Vr upon del theta plus V phi upon r into sin theta plus del Vr upon del phi minus V square theta plus V square phi upon r is equals to del P upon del r. Del P upon del r, that is the pressure changing in r direction, that is the r equation of motion. Hence we are differentiating it with respect to r, that is del P upon del r is equals to minus 1 upon r square del upon del r into r square plus 1 upon r square del by del r into bracket r square into tau rr. Actually we can prove these all equations, but it is going to quite complex and we have to use some difficult mathematical tools. 1 upon r into sin theta plus del by del theta into tau theta r into sin theta plus 1 upon r into sin theta into del by del phi into tau phi r minus of tau theta theta plus tau phi phi upon r plus rho g r plus rho gr means density into gr, that is the forces, that is the theta equation of motion. Then we are write for theta equation of motion, that is del into rho del v density into del v theta upon del t plus vr into del v theta upon del r plus v theta upon r into del v theta upon del theta into v phi upon r sin theta plus del v theta upon del phi plus Vr into V theta minus V phi square cot theta upon R minus is equals to minus 1 upon R into del P theta del P upon del theta. That is the pressure force in theta equation, in theta direction, that is it is changing in theta as we are considering the theta equation of motion. Similarly in the above equation we consider the R equation of motion, therefore the pressure is del P upon del R. Now we are going to write for Z equation of motion. This is the whole complex term that we are considering, that is minus 1 upon r cube del by del r cube into tau r theta plus 1 upon r sin theta into del by del theta into tau theta theta into sin theta plus 1 upon r sin theta into del upon del phi into tau phi theta plus tau theta r minus tau r theta minus tau phi phi into cot theta upon r plus rho g theta, that is the forces acting in theta direction, as we are considering the theta equation of motion. Similarly for Z equation of motion, that is density into del v phi upon del t plus Vr into del v phi upon del r plus v theta upon r into del v phi upon del theta plus v phi upon r sin theta into del v phi upon del phi plus v phi into vr plus v phi into v theta into cot theta upon r. Actually this equation looks quite difficult, but we can prove it. V theta into v phi into cot theta upon r. This whole term represents the left hand side term. Then we can write the for right hand side term, that is minus 1 upon r into sin theta into del p upon del phi. That is the phi equation of motion. Minus 1 upon r cube into del by del r into r cube into tau r phi plus 1 upon r sin theta into del by del theta into tau theta phi into sin theta plus 1 upon r sin theta into del by del phi into tau phi phi plus tau phi r minus tau r phi plus tau phi theta into cot theta upon r plus rho g phi, that is density into g phi, that is the pressure force acting in phi direction, as we are taking phi equation of motion, and here g is the acceleration due to gravity and density is the fluid density. Then we can come across our equation of motion in Cartesian coordinates. The term that we have derived, that is our equation of motion in Cartesian coordinate, we are writing it once again, that is density into del Vx upon del t plus Vx into del Vx upon del x plus Vy into del Vx upon del y plus Vz into del Vx upon del z, that is our left hand side term. Similarly, we can write for right hand side term, that is minus del P upon del x minus bracket into del by del x into tau xx plus del by del y into tau yx plus del by del z into tau zx, bracket close, plus rho gx, that is the forces acting in x direction, as it is the x equation of motion. Now further we can apply the Newton's law of viscosity. We apply the Newton's law of viscosity for equation of motion in Cartesian coordinate, that is for constant density and viscosity. Here we are assuming the fluids are compressible, that is for fluids moving in constant density and viscosity, means that is fluids that have constant density and viscosity and are flowing. Then we apply the Newton's law of viscosity. Newton's law of viscosity tells us that how fluid deform when subjected to a force applied to the surface and the velocity gradient within the fluid, that is in place of tau xx, tau yx and tau zx, we can put modified form of Newton's law of viscosity, that is tau xx, that is minus mu into del Vx upon del x plus del Vx upon del x. So and differentiating it, then we get the double differentiation of then double derivative of velocity with respect to x direction, double derivative of velocity with respect to y direction, and double derivative of viscosity with respect to z direction, that is minus del P upon del x plus mu into del square upon Vx upon del x square plus del square Vx upon del y square plus del square Vx upon del z square plus rho gx. Actually in place of tau xx, tau yx and tau zx, we modified it and we apply the Newton's law of viscosity and we generalize this term. Similarly, we can write it for and we can generalize it for Cartesian coordinates, cylindrical coordinates and spherical coordinates, and thus by applying the Newton's law of viscosity we get our new terms, and that we represent it as a Navier stokes of equation for Newtonian fluids. Actually we are considering these fluids are Newtonian fluids as Navier stokes equation for Newtonian fluids. This Navier stokes equations means these are the set of partial differential equations that describe the equation of motion of viscous incompressible fluids and incorporating Newton's second law, accounting for pressure, viscous stresses and external forces. So that is the Navier stokes equation. So density into del Vx upon del t plus Vx into del Vx upon del x plus Vy into del Vx upon del y plus Vz into del Vx upon del z, that is our left hand side term. Similarly, we can write the right hand side term, that is minus of del P upon del x plus mu into del V square Vx upon del x square plus del square Vx upon del y square plus del square Vx upon del z square plus rho gx, that is the x equation of motion. Similarly, we can write it for y equation of motion and z equation of motion. Now here we are consider the substantial derivative of velocity as I have already explained, that is minus of del P plus mu square del mu into del square V plus rho g. Actually here del square del is the del operator that we have already discussed, that give the divergence, describes the divergence of fluid, how the fluid is diverging or expanding when subjected to pressure, when subjected to flow. So actually here del square comes because of del square x upon del x square, because we put the Newton's law of viscosity in place of tau xx. So here the double derivative of viscosity x, y and z direction. So we simplified and we can write it at a modified pressure, that is del P plus rho gx. We can write it as del of capital P, that is the modified pressure. We can again simplify these terms. This is all we have considered for Newtonian fluid. As I have said that Navier-Stokes equation we have applied here for Newtonian fluid. So these all terms are for Newtonian fluid. So we can write the different form of equation of motion, and we can generalize the terms by combining each and every term in place and write del operator in place of del by del x square, del by del y square, and del by del z square. So density to dv by dt, that is the substantial derivative of velocity, as I have already mentioned, minus del p into minus del tau plus rho g, that is the general form. Then we put the Newton's law of viscosity, we applied, then it becomes del square v, that is viscosity, that is mu, that is viscosity into del square v plus rho g, that is pressure is as it is, and rho density into dv by dt, that is also as it is. That is minus del p, that I have already mentioned, that it is a modified pressure, that is the combined form of del p plus rho g, that is the del capital P plus mu into del square v, that is constant for density and viscosity. Actually here del operator means the divergence curl for specific cases and for things for getting more complex, that is for fluid that are more complex. Here non-accelerating term also describes the steady form where velocity does not change with respect to time, that is dv by dt. We can consider 0 here, that is minus of del p plus mu into del square v plus rho g. If we are neglecting the viscosity or forces, then we can come to know the equation, that is density into del v upon del t is equals to minus of del p plus rho g.